Right. Hello, everyone. Um, so yesterday I wasn't able to finish the code thing, but I'm just gonna move on from that, and start looking at some theory. Okay, so today I'm gonna talk about data. Just make it bigger. Data efficient RL. Okay, so I'm gonna define what it means to be data efficient, I guess, but that's gonna be like one type of efficiency we'll aim for. Okay, so yesterday we saw two environments, right? Okay, we saw Godpo, uh, where, okay, I mean, we never ran it, but like PG's was pretty easy. It runs for like maybe 40 seconds, 50 seconds a minute and figures out the optimum policy, right? So PG was pretty fast. And if you tried running the PG algorithm on the Pong environment, it takes days, all right? So with the kind of variance reduction that I was doing, where I was doing no variance reduction. PG is pretty slow. Okay. And so like a natural question appears from here, right? Like, okay, maybe Godpole is in some sense easier than Bong. All right. And we would like to like actually quantify that. And okay, maybe this was under policy gradient methods, or like the one algorithm I actually ran, but people have observed that if you choose different algorithms, right, Pong is always like a little bit harder than Gutful. And it makes sense, it's a huge state space. Um, okay, so we would like to characterize, what other problems are easy. Okay, and I guess this is not precisely defined. Um, so one way we can make it precise is asking, what does easy mean? Okay, so there are two metrics that we'll care about. The first one is sample complexity. Okay, I would want my algorithm for RL problem to have, low sample complexity, which means I should make fewer amount of interactions with the environment. Okay, so I require it few um, interactions with the environment. Actually, maybe it's better if I do it this way. Okay. Wow. Um, okay, and so what this really means, what interactions mean, is number of time uh, the agent samples from the transition function. So the number of times the transition function, the number of calls to transition function and reward function. Okay. And another thing we would kind of like to minimize is the amount of compute, which is the computational complexity. Okay, we would like it to use less compute. And compute here, GPU hours. Okay, and a very natural question when somebody talks about sample complexity and competition complexity is, why care about these, right? And, why do we want to characterize these? Is because traditionally it has been seen that if you try to analyze or characterize a set of problems which are easy, it usually also drives uh, good design of algorithms. Yeah, messing up. Okay, and also as a practitioner, if I know certain problems are just harder, then it will also mean that I should collect more data for that problem. So it also helps identify, or I guess inform how much data do you really need for your problem. But now we have much better ways of looking at this problem too. So I guess all these scaling laws and stuff like that. Um, okay. So today we're just going to concentrate on sample efficient algorithms. Okay, so when can we? Okay. I think I usually have to do this. Hopefully this will be fine now. Okay, so let's define what efficient means here. Okay, because I haven't really defined what I mean by efficient. Um, so for that, let's look at Godpol, right? Godpol has a state space which is in RT, right? So its dimension is 4. But if you look at okay, so Pong state space 16, 3, right? So if you look at basically how many unique states are there, they are of the order, exponential in dimension, right? So basically, because you have to cover all of them. But that's a huge number. So usually when we say efficient, we mean can we get algorithms okay, which interact with the environment at most polynomially many times. Okay, and this is what we'd call efficient sample complexity. You just don't want to take too many things, and so the polynomial dimension is something we feel is reasonable. But I guess first goal. Okay, so reasons we want this, okay, it takes a lot of time to collect this much data. So if it's exponential, it's going to be bad. So time investment. But also like right now we're working with simulators, so getting one sample of the data is not so hard. Like getting one sample from a transition function, one sample from a reward function is just almost free. But if you're working in a application like self-driving cars or robotics, right? Getting one data point is costly, and it's like gets harder and harder to get a unique point, right? So it's has actual like money constraints too. So it costs money. That makes it really important, right? Okay, so minimizing data consumption is just good. Okay, all right, so we would like our sample complexity to be poly in dimension of the state space. Okay, pretty good. But it's very easy to see, like in general, like if you don't change the RL problem, then you can never achieve this. So this is not possible. In general, we cannot get polynomial sample complexity. Okay, and there's a very simple RL problem here. I need to, sorry about this. Does anybody else also gets this problem where their iPad did this thing? Do you know how to fix this, or is just me problem?
So this is why I don't use iPad.
Dude, I should not use iPad anymore either now. Okay, disconnect. Hopefully, if I put it back, please connect. Um, okay. Yeah, this would not be a problem on a whiteboard or a blackboard. Okay, so hopefully this works. Okay, so this is very easy to show there are problems where you cannot get polynomial in dimension algorithms. Okay, so what's this problem? Let me just, instead of writing it, I can just show you the problem. Okay, so this problem is pretty simple, and I guess most of the people already know this, right? So, you start from a state, you have two actions, you either go left, or you go right. And so you get another state, right? And I mean, you can kind of index states by, the path. So this is basically L state, and this is R state. And then, you have two more left, right, and so on. Okay, and, this state is LL, this is LR, this is RL, this is RR. All right, and so if you look here, you have two actions, left or right, and your state space is, left, right. This is say, if this is H, then the state space is of the order, LR. So the dimension of the state space is just H. Okay, and if so I can make this problem really hard, by choosing reward is just one at a very specific edge. So for example, you have things here. I can make, say, a very specific edge, say this one, return reward 1. So only for this purple edge. And, 0 everywhere else. Otherwise, so, right? And so what it means is like, to get, even constant close to optimum policy in its value, you have to basically find this edge, right? And they're exponential in dimension many edges. So if you're just accessing transition function, even as like a generative function, right? You can just reach whatever state, it's going to take forever, right? It's going to take forever in the sense that it's going to take the number of queries you need here are exponential in h, or exponential in dimension of s.
Sorry, Gaurav, maybe this is a slightly annoying question as from an outsider, but earlier you defined complexity in terms of whether it was polynomial in dimension of s or exponential in dimension of s, right? Now, if s is just fixed as a function of time, then isn't the total number of paths I can have limited by dimension s to the power h? Because at every step I just have dimension s possible states, and so all the possible paths I can have is just dimension s to the power h, unless I'm missing the some notation, and that's technically a polynomial, right? If you look at dim s to the power h.
Sorry, what's your
Sorry,
question?
the question is, so I have, if I look at the total number of paths in a horizon s,
Yeah.
that needs to be dimension s to the power h, because every path has to pick one of dim s.
Right. Yeah, I
That's
guess,
technically a polynomial, right?
yeah, so I guess what you're saying is like, h is like a constant for you.
Yeah.
Yeah, but like, I didn't like go into all this detail. So, what you want is like polynomial in h, linear, like polynomial in dimension of s, polynomial in number of actions, and there are other like things there too. But so yeah, I mean, you can always like get away with like, by doing things like by paying exponential in h. But yeah.
Okay, thanks.
Yes. Yeah. That's a good question though. I'm being a little bit informal. Okay. Sorry, who's this? Sorry, I didn't ask
Right.
your name.
My name is Subrat.
Sudra?
Subrat.
Suvrat. Okay. Hello, Suvrat. Nice question. Okay, so great. So that kind of says, you need exponential h in general, or like, in general, this problem means you have to expend a lot of samples, right? Horizon in Carpool and other places is also pretty high. So this is bad news. Okay, so but what really happens in practice is that we don't see this kind of dependence, right? So for example, for Pong, right? Pong has dimension S. Is 10, 160 times 3. And you're not being required exponential in this number many samples because that would be huge and we will never be able to solve Pong. But there are better algorithms which solve Pong pretty quickly and they don't take exponential in that many samples. Okay, so it seems like most applications that we have, right? They have some kind of structure in them. Okay, so um, okay, in the sense that they are not really like following the asymptotics of this like worst case instance. Okay, so they don't have like this kind of worst case behavior. Okay, and so the way, this structure is like accessible to an agent, right? In practice, like, when people actually want to train our algorithms. What they do is like they impose this structure through feature vectors. Okay, so in practice, what people do, for every state, you have a feature vector that you kind of use as a proxy for state. And this is like, say, some vector in RD. And usually this dimension is less than number of states. Okay, so the state is not being encoded as just like, first state is like first box 1, everything else 0. Second state is second, so 1 and then everything 0. So it's not like this like computational basis, right? It's basically using, these features which are encoding some kind of properties of the state, right? For example, if you guys read the Shannon paper on playing chess, his idea is like, for a state, if you want to win in chess, right, you can figure out how many elephants do I have on the board? How many elephants does the uh, your opponent has, queen, king, and everything else. And if you add enough features, your value function predicting like how good a state is just like some function of those features. And you probably don't need too many. Okay. So, and we would expect this usually it's like less than S, or I'm going to be a little bit more precise now, number of actions to the horizon. Okay. So our goal now, is going to be a bit maybe too lofty, but our goal now is to find assumptions over these feature vectors, which allow us to design efficient algorithms. And these assumptions are on like feature vectors. Okay. So I'm going to define, so this is basically RL with function approximation, right? Like you have this function approximator in the mix now. And how do you get efficient RL kind of generalization using that? Sorry, are there any questions up till now? I'm going to define what these assumptions are and what precisely do I mean by this, but kind of the motivation of it. Okay. Yeah, if there are no questions, then I can continue. But maybe I'll keep typing, keep writing, and then if there are questions, just write in the chat. Okay, so I'm going to define, oh, wow. R with function approximation. Just gonna write it. Okay, so in this case, what happens is you have a state. Okay, and then there's a feature vector for that state. Oh my God.
Hello. Hi, Gaurav. I have a question.
Yeah.
So, is it the case that if you naively count the state space, it is always the exponential of the dimension and only speech
So in like worst case instance, you can create worst case instances where it's kind of happening. Yeah.
no, like in general, is there any workaround? I mean, is it possible that you count the space and it's just polynomial of the dimension without counting, I mean, without extracting features?
Oh, I mean, yeah. I mean, you can always have like, so for example, like, if your dimension is like D and each state is like just one, and like in some sense, like you can obviously create like, smaller, like when you put as like a dimension, it's already like represented something, right? So this is already like a state space with the, computational basis where you have D states in D dimension. But like I was talking about like kind of the worst case situation. And I was trying to like not be too precise, but it looks like that kind of like maybe confused people more than it should have.
I see. Yeah. Okay, I see.
Yeah, I mean it's possible for state spaces to be like linear in dimension, even smaller than that. Yeah. Okay. Okay, so we have states, and then we have feature vectors. And say these are in some RD, and we want polynomial in D sample complexity. And so what kind of assumptions can we make on it? And so one kind of assumption that people looked at is assuming like V star of S, the best possible, value starting from a state. This is like some simple function phi of S. Okay, so, you can define what simple means, but that like is one assumption that you could make, right? And then, people started looking at other assumptions and they all seem like decent, right? Like you could have state action pair. You can have a feature vector for a state action pair. And you could assume a transition function is like some simple function of phi s comma a. Whatever, the same. I can't write too many things. It's too risky. Okay, and another assumption you can make, is like q star of s comma a is a simple function of phi s comma a. Right, and so you can pick any of these, and they seem all like reasonable assumptions to think about. Like, can we get efficient RL algorithms if somehow like these features are nice, and they're nice in the form that the thing that you're looking for is easy to find. Okay, under these features. So for example, you chose nice things to look at in chess. Okay, and
So, sorry, can I ask another question? Again, as someone
Yeah.
from outside the computer science community, since you mentioned the example of chess, this is a case where you have a fixed state space, right? The state space is finite and given.
Right.
Usually, you want to differentiate between these kinds of functions. You're speaking of asymptotic growth.
Right.
For all the cases we've spoken about so far, like Pong and Cartpole, and these are finite state spaces. So are these really like sharply defined distinctions that you're speaking of?
Oh,
Simple.
I guess like the kind of asymptotics I'm talking about is like as you grow in this, like if you change around in the problem space. So chess, Pong, I'm thinking of like, features, the Pong features that I created, they were probably like lesser dimensional features than the features I probably need for chess versus I need for Go versus I need for learning language.
I see. So you're thinking of an algorithm that will work across problems. You've not fixed the problem.
Exactly. Exactly.
I see.
Exactly.
Okay.
And that's where asymptotics comes in. And I'm trying to like kind of, I mean, if I go into the level of like, oh, I'm talking about chess or Pong, then it's like, yeah, maybe there are other ways, but like I'm looking at the level of RL where every, arbitrary, like abstract way, every state has a feature associated to it.
Right. Okay. Okay. Thank you.
But good question. Yeah. These are like things I have not defined precisely. But when talk about computation tomorrow, then I'll actually define it more precisely too. Because there, I think if you don't talk precisely, things can get pretty wonky. Okay. Right. So, okay, so I talked about so many assumptions, right? You could pick restart to be like some simple function or so. So, one simple function is linear, right? So, we could assume any of these functions were linear. And it turns out like people have looked at these problems a lot. So they know, like, assuming that transition function is linear, I'm not going to define precisely what I mean by linear, but it's a vector. So there's a matrix kind of associated to it. Uh, this thing being linear is kind of like a really, really strong assumption because this implies that Q star of S and V star, sorry, Q star of S comma A and V star of S is linear too. And some of the features, but so it's a really, really strong assumption. You get much more than just these optimal values being linear. So the simplest assumption here in some sense is like assuming like these optimal value functions are linear. Maybe there's something similar, but it's like a decent start. No. I really wish I knew how to fix this. Okay. Okay. I'm not going to write too much, but we're going to look at linear V star. So we'll assume that, this V star function is linear. And what that means more precisely is that there exists some theta star in RD. Okay, such that V star of S is just the inner product of theta star and phi of S. Okay, so, and this is what I mean by, having good features. So your features phi of S are so nice, that your value is just this linear function of it. You don't know what theta star is. This is unknown. And there's some norm bounds on it, say norm is less than 1. Okay. Okay, and then the question is like, okay, if you assume, say, this is true about your features, can you design efficient algorithms? Yeah, I cannot talk too much. It's too risky. But so can you design sample efficient algorithms given these things? And this was like a really cool result. I would say, no, this is still not enough. And so this was a breakthrough result. By Rise Otila and Chava. I don't know how to pronounce Chava's last name, but I think he'll be fine, right? So it was a really good result. The construction is pretty awesome. So, and if you are interested in theory of RL, you should definitely read this paper. And then there was, at the same time, another result kind of showing the same thing by Wang, and Kakade. Okay, so there are instances, and their game is basically a game over a hypercube, where even when you assume that you have linear V star, so you have access to these features, says that your V star function is linear in it. So it's trying to solve just like a linear problem. Even then, you cannot get polynomial in D sample complexity. Okay. Any questions about this? Because I'm writing little, so I don't want people to like, if it feels like maybe it's too less like formal, then I can write more stuff.
Yeah, I think a little bit more formal would be good.
Okay. So I can just write more.
Sorry, Gaurav, are you sure your tablet is not plugged in to charge?
It's not plugged in.
Okay, then it's strange.
Okay. Okay, and this basically means only polynomial in D many calls.
Hello. Ah,
Yeah.
yeah. So initially we are only given the problem, right, where there is a state space and the MDB setup. So from the state space, how do we go about finding what small d should be the, like, how do we get a hold on what small d should be in the first
Yeah,
place?
so
Forget about phi. Yeah.
yeah, so I'm saying, like now when somebody gives you an MDP, they also give you a way to compute features for a state. So somebody, you're given a state, and if you're in some state, you can ask this oracle, give me, the feature for this state. And it will return a vector to you, and the length of this vector is D. And also, it tells you maybe a priori that, it's gonna be a vector of dimension D.
No, no.
So
So your entire point was how do we go about finding good phis, right? That are like good feature vectors that uh, like give us good results in some way.
Oh,
Uh,
actually,
on the-
no. So, so you are like given features phi of S. So you're like already given access to these features. So you don't have to find them. Question is like somebody even gave you these features. So that's why like this result is pretty cool, because it's saying like, even if you give me features, this is not just like the traditional like least square regression problem where, you have phi of S. If you had V star of S, yes, this would just be linear regression kind of thing, right? If you're trying to learn just theta star. But it's like a chicken egg problem to figure out like V star, you need theta star. So you still have to like interact, but still, I mean, it seems like this problem space has been restricted, but somehow it's not been like restricted enough.
Hi, so what exactly features are we given? We are given phi of S and also phi of S comma A.
Oh, so you're given access to an oracle. So whenever you're in some state, you can ask that oracle. Okay, let me just write it more formally. So, recall we had this setup where, the way we interact is, agent starts in,
Or if I Googled a bit, it seems iPad has some grounding issue. If you touch the metal parts and hold it for a while, it will go away.
yeah, I'm trying. This is like the only thing it never works. Okay, starts in state. Wow. Okay, I'm gonna take a, way to fix it thing. So let's see. Can I fix it? Maybe I should put it on charging.
Hold the metal parts of it for a while of your iPad.
See. Okay, hopefully this fixes it. Okay, that seems a little bit better. Okay, so this is the interaction model, right? Your agent starts some state and then does it loop, right? So for h equal to 0, 1, h minus 1, agent observes state sh, right? And so this is basically the difference now. So now it has this, another thing it can do. It can query some oracle, right? And you can query like phi sh and phi sh comma a. Okay. And every time it accesses this information, it's using compute. Okay, and then whatever the rest of the thing is, you choose an action based on these features or whatever, and then, continue. So does it make sense, Jatin?
Hi. Yeah. And now the assumption on linearity is that T of S comma A is linear in this phi of SH comma A.
So the assumption is like V stars, the optimal policies of S is linear in these features phi.
And something else is linear in the phi of SH comma A.
So I mean, yeah. So I guess I was talking about multiple different. So right now, like the thing I'm talking about, you only have access to like these features.
Okay, right now just this. Okay.
But yeah, okay, maybe I should have been more clear about the setup. But I have very little time because I have like 10 more slides. So more than that.
Yeah.
So I guess I'm gonna hurry up.
Yeah.
Okay, so they show that basically if you have even access to this good features, it's not enough. Like still the space of problems is large enough to have like these worst case conditions where you really have like exponential and d-many sample complexity. Okay, so let's pick the next best. And that's basically, assuming both Q star and V star are linear. So what does this mean? So you have two set of features now. And there's like some kind of interaction between them. So linear V star means the same thing as before. We have access to feature such that there exists theta star in RD such that, wow, I feel like I can write pretty normally now. Thank you. Star of S is equal to theta star MS. So there are good features psi of S like this. And then there's other features. So there exists W star in RD such that Q star of S comma A is linear in some other vector and those features. So I'm basically, this is basically saying there exists known features phi S and phi S comma A that you access using those oracles. Okay. Perfect. And so the result I'm going to talk about today, to kind of like show all the techniques, is going to be this result. So you can get sample efficient algorithms in this setting when both B star and Q star linear. Okay, and there are many more settings where you can get this. So, okay, so for example, it is linear MDPs where you assume, the transition function is linear. I mean, obviously, because that implies V star Q star is linear, but I guess there are other methods of like computationally efficient algorithms too. There's linear Bellman complete. So these are like various other linear mixture models. I don't know how many people know about these all, but so there are these all different models, and you can get sample efficiency in all of them. Okay, but surprisingly, there's like just two algorithmic ideas which get you like polynomial sample complexity in all of these. So there's one single algorithm which basically works everywhere, right? And it's based on these two ideas. So there are only basically two algorithmic ideas you need. Okay, one is of optimism. The other is Bellman equations, which you use for, I guess I should say, consistency. Okay, and these, these solve all these. But you can use it to prove sample efficiency in all these settings. Okay, and second thing which happens, which is cool, is that once you use these algorithmic ideas, really the analysis is like just reducing this RL problem that I actually haven't defined right precisely, but to finding the optimum policy, to another math problem, which is also a cool math problem in itself. So the plan for the rest of the time I have is I'm going to first talk about this math problem. And if you know how to solve this math problem, all the other papers on understanding like how linear MDP works or linear Bellman complete works or anything will be just like, reducing that problem to this math problem, because you can use this math problem to get sample efficiency in all these settings. So I'm just gonna first go over this math problem. And then I'm gonna show you for linear, Q star V star, how you reduce RL to this problem. And then, so I'll talk about optimism and Bellman consistency. Okay, so the math problem here is, there are many names for this. But like, for example, if you want to search for this after the talk, you should search for eluded dimension. Okay, so this is started by Dan Russo, the cool guy, and Benjamin Van Roy. Okay, so let's just quickly go into this problem. So I'm gonna first define like independence under linear functional class. All right, so this is not like the usual independence from linear algebra. It's like, okay, maybe I should say like scaled independence. Okay, so we say a vector of norm one. So SD, it's just a d-dimensional vector where norm of x is less than or equal to 1. Okay, so we have a vector of less than 1 norm. I'm going to say this is epsilon independent. Oh, problem is coming up. Of a sequence of vectors. The x1, x, say, n minus 1. Each of these is a vector in SD. Okay, I say a vector is independent of sequence of other vectors. If there exist, theta, theta star, think of them as linear functions, right? In SD, such that, okay, I'm going to write down the equation. Basically, they agree on x1 to xn as, whoa. Okay, so if I look at xi, on xi, theta and theta star are kind of like agreeing. So they're all agreeing on all like 1 to n minus 1. And they disagree on x. Okay, so they theta and theta star agree on x1, 2. No. Hold the bed. Okay, so they agree on x1 to xn minus 1, but disagree on x. Okay, so does this definition make sense?
Give some illustrative example, like of some sequence which is independent and which is not.
Yeah, like, I mean, like, for example, if the vectors are independent, like, for example, so the basis vectors, they're going to be independent,
Yeah, I think that's kind of clear. Yeah.
right?
Yeah.
But they're like, so the only like one way of kind of like creating these things is like scaling. So let's do like 2 to the power, I want to do make small. So things which differ by 1 over epsilon, right? Like So if something is epsilon, right? Another one is like 1. You can like get like less error on like this epsilon 1, but you will probably get bigger error over. So these two are independent. So epsilon, if epsilon 1 comes before.
Right, yeah.
So there's like a scale thing too. So you can
Yeah.
fit like basically like log 1 over epsilon many things in one dimension.
Okay, great. Got it. Excellent. So in general, for D dimension, it's more like D times log 1 over epsilon, or
So good question. That's the problem that we want to
okay,
solve.
okay.
Right. So that is exactly true. So the example I just gave you, it at least tells you like it should be at least that. But what's an upper bound? An upper bound is also like a constant of it. And so that's the thing I'm going to prove in the next part. So that's the problem. This is a very common proof technique. Like this is through like volumetric. So you can use it to prove like other things too. Like people find covers using this. Okay, so so the question, like as Jatin said, is if you have a sequence, x1 to xn, where xi is epsilon independent of x1 to xi minus 1. So anything is independent of things before, how long can the sequence be? Meaning, what's the upper bound on n? Right? And what we're going to show, sorry, I don't have time to build the suspense, so I have to just tell you the answer, right? So you can show that, this is basically O of d log 1 over epsilon. Okay, so I'm just going to quickly do the proof. But this proof should be similar to like a proof of like ellipsoid methods and other things. So it might be known to a lot of people. Okay, so basically the way this argument works is that whenever you think of these vectors like holding on to some space, right? These vectors, they're like they have a covariance matrix, right? That has like some determinant. Like think of that as a volume of that body, right? And basically what happens is like when you find this epsilon independent vector, like you add to x1 to xi, you add xi plus 1, right? That's like kind of like adding a new dimension to this object, right? So this volume basically grows like by a constant factor. And like this is basically true. Like if you're adding like small norm vectors, you cannot like grow volume of a body many times because the volume like is like should grow polynomially in like a d-dimensional space. Okay, it can only grow like exponentially in D. It cannot grow further than that. It cannot grow exponentially and I guess the number of points. Okay, so I'm gonna formalize that. But it's just like a volume argument. Like every time you find a new direction, it's gonna explode the volume, but you cannot explode the volume in a lower dimensional space many times. Okay, so to kind of look at the volume, I'm gonna look at the covariance matrix. So I define like I have these vectors xi's, look at the covariance matrix. And just to kind of like start from like some finite, to kind of look at this like scale, we have a scale here, right? We have epsilon square scale. So because I know the proof, so I'm putting epsilon square over 4 here. It's something magical. Why did I choose 4? But sure, like, so there's like some scale that I added, and then I'm looking at a covariance matrix on that scale. Okay, and so we know that xn is independent of, or I guess I'm looking at sequence. Maybe I should choose xi here. It's gonna be so ugly. Okay. Okay, so if xn is independent of x1 to xn minus 1, okay, that meant that there exists like some theta and theta star such that they agree on xn. Sorry, disagree. So if you look at the square, this is more than epsilon square. And they agree on the other vectors. Okay. And so to kind of like relate it to like the properties of Vn, I'm just gonna write down a program. All right. So so let's look at this program. Okay, I do max over say rho. Okay, so it's a optimizing a linear function with quadratic constraints. So such that, a norm of rho is like less than 4. Okay, I'm writing it weirdly, but like that's the norm squared, right? And so our theta minus theta star, they're norm 1 vectors, right? They are a solution. So rho equal to is a solution to this, constraint problem. Okay, so that means that this thing is going to be at least epsilon, right? Because if I put theta minus theta star there, this is xn, it's the first line, so it's more than epsilon squared. So the root is like epsilon, and it satisfies these equations. Okay, does this make sense? I did it pretty quickly because short on time.
Yeah.
Okay, perfect.
You're good.
Okay, and okay, I'm just gonna kind of like put this in together because this is same as, or a little bit better, where I kind of like merge these two equations. So that sum of I equal to 1 to n minus 1. So this is where epsilon square root 4 comes. I just want to make them the same scale. Okay, so anything which satisfies the upper constraints will satisfy the lower constraints, but the other thing might not be true. So it's slightly bigger set. Okay, and so this is a PSD matrix. Okay, and this is exactly Vn. So this is basically saying that the value of this program is just root 2 epsilon square xn's norm in Vn inverse spaces. Okay, so this step is, I'm doing it really quickly. So I'm just gonna show this. So, we had max rho n subject to or transpose V rho less than 2 epsilon squared. Okay. And what you want to do is like you want to have like norm constraints should be like norm constraints on rho, and then you would say like the best thing you can do to optimize the linear function is like be in the direction of the function that you're optimizing, right? So you can say like this program is same as maximizing, but you kind of look at the root because PSD, so it has a root. Okay, and then you kind of like replace y with this, and you basically get exactly the same thing, right? So you get so this norm has to be exactly root of 2 epsilon squared xtv and inverse xn. To make sense? Just like after that, it becomes max so v inverse. So is inverse y. And if you just put it in there, it's transpose, you'll get the right thing. Okay. All right. Okay, but what this means is that norm of xt in VT inverse basis is going to be more than half, right? Because this has to be more than epsilon. Okay, so if you look at the volume of Vn, right? So if you look at determinant Vn, okay, by matrix determinant lemma, right? It's going to be determinant of Vn minus 1 times 1 plus exactly the term, the norm of xt in the Vn inverse basis. It's basically saying, if you go in direction that is not represented by my covariance matrix, then you kind of like increase the volume by the norm of this direction in the inverse base. Okay, and so this becomes more than 3/2 determinant of Vn minus 1 because, it's more than half. Okay, and if you kind of do this like recursively, it basically says like determinant of Vn is more than 3/2 times n minus 1 norm, or like determinant of epsilon squared over 4 identity, which was kind of our like scale. And so, determinant is product of eigenvalues. So this is just right. Okay, so your determinant is like growing exponentially. So this is exponential in n, right? But the kind of things I was saying before, if the volume of an object in the dimensions, it's a d-dimensional object, cannot grow, through these kind of processes exponentially fast in n, and that to show that basically use AMGM inequality. Okay, so determinant, of a PSD matrix is product of its eigenvalues. And trace of M is sum of eigenvalues. Okay, so this means, that determinant, like Vn, right? So that's the PSD matrix, is gonna be like less than trace of Vn. D Property. Okay, so like because oh my. On. Okay. And so what's the trace, right? Actually, trace is much easier to compute, right? So trace of Vn. Okay, Vn is see, some so x and transpose plus is epsilon squared over 4 identity. Trace is linear. So this is, at most, the first terms are just like trace is the norm. So norm is less than 1. The n minus 1 terms. It's like something like order n minus 1 less than n plus epsilon squared d over 4. Right. And so what we're basically getting by using these equations is that 3 over 2, which is this determinant, should be less than n plus epsilon squared d over 4 divided by d over d. Okay, and so this is some polynomial. And then this is something exponential in n. So it cannot be too big. And basically, if you solve this equation, you get that n can be at most d log 1 by epsilon. Okay. So you cannot find too many epsilon independent vectors in a space. It's just constrained by volume. Good. Do people have any questions?
No, I think this was pretty clear. Very good.
Okay, awesome, awesome.
I think you can take like another 5 minutes. Maybe you can now see the connection between RL and this problem.
Yeah, so let's see how many slides was I planning to do. 1, 2, 3, 4. 4 slides. So 5 minutes. So what I should probably do first. Okay. Yeah, let me quickly do this. Okay. So let's talk about the algorithm. Okay, so I haven't actually told, what's the algorithm which is going to get a sample efficiency, right? And so that algorithm is basically going to be the reduction too. Okay, so basically the algorithm is based on these like supervised learning theory ideas. So we start with like some concept class. So each element of this class, is like pair of QV functions. They are like some candidate hypothesis. So you have this set of hypotheses, and every time you interact with the environment, okay, so what you're trying to do is like you have this set of candidates which can be Q star V star, and you want to figure out which one is Q star V star. So every time you interact with the environment, okay, you get some information about Q star V star. And what we'll see is like, in some sense, like this is actually just a constraint over the hypothesis space. So, if the space is H, it's some constraint over H. Okay, so I'm going to draw linear, but, it's going to be constrained like this, saying, everything has to be on this side or something like that, right? Okay. And so basically the algorithm is going to look like this. I'm going to run this algorithm for some rounds. Okay. I'm going to say, run a policy phi. This is going to be induced by some QV candidate. Okay. And I'm going to choose, one which is, which appears to be the best. Appears to be optimal, according to my current experience. All the things that I've seen up till now about the environment, this pi seems to be optimal. I'm going to choose that. And then, either I got lucky and pi is optimal, or, I gain experience, either, or I find evidence, and in some sense, certificate of, suboptimality of pi. Okay, and this is basically what's optimism. And this is Bellman equations or Bellman consistency. So Bellman equations is going to be like kind of like providing us with a certificate that the kind of policy you're looking at is not optimal. And we'll like figure out like how to turn that certificate into like decreasing the set of all spaces, like set of all QE functions. Okay. Questions? Oh, how much time do I have? I'm such a slow talker, but
This will work if we cut it fast enough, right? If we cut the hypothesis class fast enough.
yes, and that's the math problem.
I see.
Yeah. Okay, so let's look at the Bellman equations. Okay, so Q star V star. Bellman found these like conditions that Q star V star functions have to satisfy. So they satisfy the following equations for all S. Okay, so recall like I'm kind of not writing H, in the definition of Q star, but it's important, right? V star and Q star related because the best thing to do after you take an action is basically what V star tells you. So this is basically exactly where our H is sampled from DSHAH and SH plus 1 is sampled from okay, so if you're in some state, SH, take action
I think there's something
AH.
which Eric did. So I think don't need to go over this. But you want to put a gamma somewhere? Like, is there gamma in the second term or something?
Oh, yeah. So I'm not like the whole setup I
Okay,
did.
okay, okay, great. Sure. Yeah. But I think these people would have seen, I think, because Eric Mazumdar already did this in another context. So
Okay, perfect. So now, you can write this as, expectation. You move the expectation on the left-hand side, it's like some equation, right? That Q star has to set, and V star have to satisfy, right? So it's some equation, but it's an equation, they're like S, A, many equations. Okay, and what you can show is like actually these are linear equations in the features. So the phi s and phi s comma a, these equations are actually linear in these features. And basically, because of the linearity, this problem basically reduces to like finding these like independent vectors or epsilon independent
Yeah,
vectors.
so I guess what's going on is that your theta and theta star are the two things which you want to know to find the optimum Q star and the V star. They are the two unknown parameters, and now essentially in each iteration, in each round, you either keep winning, but the thing is that if at some place you fail, then means that you have found a long sequence where you were waiting for a long time and then you failed. But that's even
Exactly.
too long, and that's it. Yeah.
Yeah, the thing is like there are like little bit like subtleties that we kind of like glossed over. Like there's like some notion of like optimism you need.
Yeah.
So this can only like verify like whatever you just said only verifies if something is optimal or not.
Yeah.
So to find it, you need to do this trick with optimism. And so, but yeah, all the main ideas are done basically at this point. So I just need 1 more minute because I want to talk about tomorrow.
Yeah, sure.
Okay. So what we saw today is like if your state space is subset of RD, then you can samples you need can be polynomial in D, right? And for that, there are many assumptions. You could be linear Q star, V star, or Bellman complete, and so many others like linear MDPs and so on. You can get polynomial sample complexity. So you only need these many samples. Okay, and another important thing is like, this is basically saying how many times you have to interact with the transition reward function, how many chess games do you have to play. But then you also have to ponder, right? Like you have to ponder, like I played all these games, so now what's the optimal policy, right? And so the question is like, how long do you have to ponder? And so that's like, how much compute do you need? And so a lot of people have worked on this. And so the one thing we know is that if you assume that the transitions are linear, then you can get efficient compute. But like I said, like transitions being linear is just a really, really strong assumption. Okay, so I guess the question would be, can we find, computationally efficient algorithms? And so with these kind of results, we were hoping that we'll design computationally efficient algorithms for, the simpler settings like linear, V star, Q star. Okay, and okay, I mean, this kind of makes you feel like maybe, yeah, we can design computationally efficient algorithms for it. But also like, from supervised learning, we know that, if you are trying to learn linear function, you need only like in D dimensions, and you need only D many samples. And you have efficient algorithms, right, to do this like linear regression, stuff like that. So can you do something similar for RL, right? Like you have trying to learn this linear function, and maybe the algorithm is a little bit complicated because your setting is slightly different, but you showed that, okay, there's just a scaling on D, right? D, replace D by D log 1 over epsilon, and you got the sample complexity. So can you also get computational, similar kind of like D dependence? So that's going to be the goal. Can we design efficient algorithms? And tomorrow I'm going to show that actually somehow this problem is a little bit different than supervised learning. So we might not be able to do efficient algorithms here.
Okay. Thanks, Gaurav,
Yeah.
for the nice class. Maybe we'll break for tea, and anybody has questions, they can keep asking. I'll leave the mic here. So I do have like one question. So,
Oh, perfect.
So here, what do you think is the answer here? Like, do you think that they should exist? Like, what's your feeling about this?
Oh,
Your feeling.
so I mean, this is the, kind of what I did in like my 5 years of PhD. So we solved this problem. Yeah. So
So-
so we showed that there's actually like hardness here.
Okay. Okay.
Yeah.
I see.
But there's more problems here that we
Yeah.
don't know answers of that I'm going to talk about tomorrow.
Right. Yeah. And yeah. And also, I think there's this whole other area of stochastic approximation.
Like, what do you mean by that?
Where people try to find fixed points of a function which you can only access using estimates. So you only see noisy versions of the function, and you want
I
to find
see.
its fixed point.
I
So
see.
there is whole group of people who reduce RL to that problem, and then they use yeah.
And I guess the kind of thing they're approximating is like this Q star V star functions. I mean, I guess
Yes, exactly. Yeah.
those fixed point theorems.
Yeah, exactly. So they say that the Bedman operator. From that you can get this fixed point problem, and here, because essentially you have the same thing on the left and the right, except
Yeah.
that you have h plus 1 and h. So
Yeah.
it's essentially a fixed point problem, and yeah. So
And so are they using like some kind of function approximation too? Like, I guess, where is the approximation coming from? Like, is this still like in the world of like total number of states times total number of actions, or is there like lower dimensional thing going on?
Yeah, that's the thing which I'm not sure about.
Okay.
Yeah. So, but I think would be good to understand the connection between these two communities. So, yeah. So, yeah.
I think the biggest problem I know in all the work going on RL, or like the one big problem that is very important but people don't know how to solve, is the fact that if you go to any like application, ChatGPT or like all these games, right?
Yeah. That's
A
what
lot
they
of
do.
them are using policy green methods. They're
Right.
using PPOs,
Right.
right? So design, like understanding sample complexity and like comprehension complexity of those things is a little bit tricky.
Really important. Yeah.
Yeah, I think there are ways. I mean, I like, I'll tell you more about this problem offline, I guess.
So,
After.
for policy gradient, do we know things like this, like sample efficiency, compute efficiency? Do we know anything about that?
So with function approximation, it's really hard to do.
Okay, I see.
Yeah. So like, if I ask like what happens if I mean, you have to first talk about like, your policy being linear or something like that, right? And then things become a little bit hard. I I think how to do like the cartwheel problem. That's like one summer I spent with Chaba. But we never wrote it down, and I mean, we never actually figured out the whole problem. So, but I want to like get back into it too. So I feel like those are pretty cool problems, but they just get like progressively really hard really quickly.
Right. So,
Yeah.
so yeah. So, yes, to summarize, so for PPO we don't have such results. Like we don't know sample complexity poly-D.
Like even like PPO like is a little bit complicated. Like even like simple like policy gradient stuff, we don't know.
Oh, okay, yeah, okay, even really simple stuff. I see. Okay, got it.
Yeah, and there is like even more
Advanced.
amenable algorithm, which is like really in between like these algorithms and policy gradient,
Okay,
uh, natural policy gradient or something like that.
see,
I don't know if, but this those algorithms are like slightly easier to analyze,
see.
but yeah, don't know anything about them either.
Okay, okay.
Yeah,
I think Tirthankar has a question.
yeah.
Hello, Gaurav. To reiterate
Hey,
my question from before, you said that the feature vectors are already given by the oracle. So
yeah.
my question is like they can't be some random junk, right? Like from the state that somehow there has to be some meaningful feature vector. So how exactly do you get the feature vectors? That was my question.
Oh, I guess this is like an assumption about those features vectors. So are you asking um, say that you make features for chess? How do you know V star and Q star is satisfied?
Yeah, so essentially, like when we frame the MDP, we have state space, we have like action space, and which depends
Right,
on the rules of the chess transit,
right,
whatever. Yeah,
right.
all those things we have. But from the state space to get this feature space, I think some clever this thing has to be there, right? Some
Yeah, so you're asking like how do I build features
yeah, yeah, yeah.
that my problem becomes linear and then I can solve it.
Right.
So like even if it's not linear, it's going to be like some polynomial.
I see. The value function will be some polynomial. No, 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 no.
Right?
What
I
will
mean,
be the
it's gonna be like, I mean, at worst case, it's gonna be like, so it's gonna be some function, right? That
right?
you agree? And that function could be like, okay, maybe super complicated, right? But like there's some polynomial approximation of it or something.
No, so the state in itself, it is like an unstructured quantity. Like state doesn't have the feature
Yeah,
space is basically the structure that is being given to the state.
yeah. So I guess the kind of thing I was thinking about was um, like say take Pong,
Okay, yeah, sure.
right? And then you have a CNN,
I see. Okay, yeah.
right? So this is like the way I kind of like also justify this. So what you do is like put a CNN in front of it, and then it outputs like given a state outputs value of the state. Okay, so
Okay, so the
actually maybe I can draw it. Let me just
pixel
draw it.
value would be the feature space in this case.
Exactly, exactly. So I'm saying like you have this thing, you have this value function you're trying to learn. This basically this last layer, right before it, it's just some kind of like features that I'm saying. If somebody gave to you, you could solve it. But I mean, it's not a substitute for like in that sense, not like complete algorithm, right? Because it assumes that you have access to these features.
Like for example, this wouldn't have been an issue if we use neural networks. They kind of learn it on their
Yeah.
own.
It's just like then the theory is like you also have to figure out how to learn these features, and there's work on it. So if you look at like this algorithm called like Flambe by um, Akshay Krishnamurti, Shyam Kakade, and others. I think Cyril is on also in it, and Nang.
So what
So
exactly is their work on?
so they basically show that in some other setting, so it's not going to be linear Q star V star, but like some other setting where you also have linear features, you try these features that you're trying to like, you don't want to assume that they exist. They basically also find those. So as they exist, you don't know them. You find those features.
Oh, interesting. Okay. Thank
Yeah.
you. Yeah.
Yeah.
Hi.
Hey.
So I have just one question. So can you please explain me once more that how have you reduced that RL problem to the math problem? Because
Oh, I did not explain that, and that is not like trivial. So it takes like maybe 2-3 pages.
Okay.
So the reason you didn't understand is because I didn't explain it. But if you look at the notes
Okay.
for this course, I've actually written it down like much more formally, and there's a reduction there.
Okay. Sure.
So because like the one problem with that reduction is also the fact, like I said, like, it might be clear to some people like how to do like check or verification, but I haven't explained like how to actually compute the good policy.
Okay.
Yeah.
Thanks.
Yeah. Sorry, what's your name?
Shantanu.
Shantanu. Hey, Shantanu.
Hi.
All right. Are there more questions or should okay, maybe I should just leave for the day. Have fun. Oh, I should check the chat.